Okay, so little bit we have seen single phase transformers, then we have seen your 3-phase induction machines, only in brief, right. Most of the time for induction machine we have spent to make an approximate or equivalent circuit, right. So next this will be the last topic for this course. So it will be discussed in a I mean not in detail, in brief at first year level, some ideas you will get, right. So we will start with DC motors. So things are quite simple, So basic type of DC machine is that of commutator type. This is actually an your alternating current machine, but furnished with a special device that is called commutator, which under certain conditions converts alternating current into direct current, right. Actually DC voltage or DC current means, suppose it remains constant. So in your what you call, when we generate the power it is AC, but we use some kind of mechanism such that it will your what you call, it will be converted to DC, right. So now we will study your DC motor, but principle of a generator very simple it is. Whatever write up is there, it is okay, just I am telling. So when we studied that your single phase AC circuits, at that time we showed that how EMF is generated. So this diagram also, look, this is your what you call, this is, if you look into this, these two, if you look into this, this is a magnet, this is N and S, these two poles are there, say, and then suppose a coil is revolving in clockwise direction, right. This is the motion is given in a clockwise direction. This is one side of the coil and this is other side of the coil, only one turn it is shown. Now when the coil is in like this position, right, so flux moving from N to S and it is revolving. So at this position your what you call the flux linkages will be maximum, and this is the other side of the coil, the back coil, and this is this thing, it will be just out of this your what you call these poles. So there will be, assuming there will be no flux linking here and nothing will be here, and only under this condition flux linking will be maximum if you have only one turn. If you have more number of turns, so this position the flux linkage will be maximum when it is revolving. Now when it is coming, suppose it rotates 90 degree, at that time this position, suppose it is moving like this, so this position will come top and this position will come to the bottom. At that time flux linkage will be 0, because this will be now at that time outside of this, right. So at this way it is revolving and a voltage will be what you call, and alternating volt EMF will be induced in that coil, right. And this is your external connections, whatever it has gone to this side, suppose by some mechanism you have connected, right. So this is actually, and this is the from N to S, so that is why this direction of the flux, and this is your what you call current is given and it is alternating. Only thing is that EMF will induced only these two parts, these two are coil sides and not on the back coil, not here, because this is the main portion and this is the position, right. This is the position that where that maximum, that this will link the maximum flux and EMF will be induced maximum, right. So this is a simple thing. So this is your elementary generator. Now this is what I says, that this and this EMF is basically Faraday's law of electromagnetic induction, right. And this whatever I said. Now question is that therefore the basic essential parts of an electrical generator are, right, that a magnetic field, now a conductor or conductors which can also move to cut the flux, right. So a magnetic field is required and your what you call, and conductors which will also your what you call, which can also so move to cut the flux. Now this is your horizontal position in this diagram, right. Now this is another diagram where this is the position, the vertical position. In this case, although diagram I have taken this, all these things I have taken from book, right, but this is N pole, this is N pole, this side is L and this side is M, right, and this is your N and this is your P, already marked here. Now at this position you will find, say you can say it is a neutral position. At that time this is one side of the coil, this is other side of the coil, this is the back side and this is your, it is coming out. So only voltage will be induced here and here. So at this position, say it is 0 position, right. So at this position there is no flux linkage at that particular instance. It is revolving, it is given, it is revolving, say by some means you are making it to rotate, right. So it is revolving. So at this position the voltage induced will be 0, because no flux linkage here and here at this position. So this, that means, let me clear it, that means your this thing your this thing. So, at the 0 is not marked here. So, it is the 0 position, then 1 2 3 this way it has been marked in this figure. So, this way when it is revolving, say 0 to your 180 degree, when it rotates 180 degree, this is the same way we have seen single phase machine, that alternating EMF. So, 0 to 180 degree it will be your this plus, right, and next 180 to 360 it will be minus. That means, this will your what you call 0 to 360 degree, it will, if it complete rotates. So, this will be positive side induced, and this will be the the positive voltage will induce, and this is the negative, right. So, this is a pure alternating when it is moving. Whenever we have given that your what you call that sinusoidal and phasor and that EMF equation at the beginning of the single phase circuit, the same philosophy, right. So, it is revolving, it is marking 1 2 3 4 up to your 0 11 and 0 it is marked just to make a 30 degree shift, but it is revolving in that your what you call here in that your what clockwise direction. So, if it, and this same way the voltage will be induced, right. But if you look into that, this is that instant, and this is a particular position, right, instantaneous position we call, when this ln when it will come on top, when it will come on top, and this pm your plm this is lm, and when this pn will come to the bottom. So, at that time it will be like this, right, and again when it will go to another 180 degree, then your, let me clear it, then again it will be your what you call the same position. So, this time it will be your what you call your voltage will be induced as negative 1, the same as alternating one, right, as it is revolving. So, and philosophy behind this single phase AC circuit at the beginning we have seen. So, this is AC. Now, our objective will be to convert this negative to DC. That means, if you bring like this, so all will be your what you call positive. So, no question of alternating. So, then by some mechanism, then we can get that your what you call DC current instead of your AC current or your AC voltage, you will get DC voltage or DC current. So, in that case what? So, this is your what you call that alternating your EMF induced, right. Now, next is the conversion of alternating current into direct current by means of a commutator. Generally, that commutator actually in a your what you call in a DC machine you have several commutator segments, right. So, basically in order to, before going to that figure, in order to convert the alternating current to DC current, it is necessary to employ a mechanical switching device which is actuated by the mechanical rotation of the generator shaft called a commutator. So, in this case what will happen, that this is your some instant, this is some instant, say this is the position of the coil, this is your NP and this is your LM, this is the back side of the coil, and here suppose this point is A, this segment and this segment is B, these two are the commutator segment. This commutator segment actually they are insulated from themselves, right, and actually the shaft is there. If you look in your college, if you see the laboratory, the open your open DC machine, then you can have a better look. And this coil, this is the, suppose this is a brass generally made of carbon, this is the minus side and this is the plus side, this is the N pole and this is the S pole, right. And in that case, suppose it is rotating in this way, the clockwise direction. So, in that way, this one side of the coil, right, one coil side is fastened with the segment of the commutator A, and other side and it is a plus, and other side of the commutator connected to segment side B, right. So, in that case, when it is revolving, suppose the way we saw alternating thing, the mechanism is such that when it is revolving, right. So, up to your first 180 degree, the voltage will be like this. After that, what will happen? This is now this coil side is connected to A, because next cycle it will go to the negative side, automatically it will change its position and go to the negative, your what you call negative side of this. These two are called your what you call that your that DC machine brass, right. And in that case, what will happen? Here this coil position from plus, when it will go to the negative voltage induced, automatically it will be connected to the negative side by this mechanism. So, this is actually show only two commutator segment. In DC machine you can find thousands commutator segment. If you look into this, that all commutator segment are insulated, right. So, in that case, what will happen as the next half cycle when negative voltage will be induced, automatically this coil side will be shifted to the negative negative side, right. So, in that case a reverse will happen for other coil side also. So, that means your voltage will be always your positive. So, this is actually mechanism for your DC machine. DC machine actually generates alternating voltage or current, right, but due to this commutator and this mechanism actually this your polarity, this minus and plus polarity will remain as it is, right, only at at that particular instant, or you can say that when it is crosses the neutral zone, right. So, at that time what will happen that when negative voltage will be induced, so this coil automatically will connect to the here, automatically move to the other one, and a reverse will happen for the other coil side. So, such that voltage will remain positive. So, for DC thing whatever we know, suppose this is our time, suppose this is your what you call the your and this is your my DC voltage, this is my DC voltage. Whenever we draw, it is like this constant, right, because with time DC voltage is constant, but in a DC machine you have several segments, you cannot unless and until you see in your exact your what you call that figure, right, then this is actually apparently it will be apparently it looks like a DC your straight line, but basically it will have a I am drawing it here, it will have the very small ripple, it is very small ripple like this. I mean it is positive side, all the ripples will be positive side. I mean just hold on, if I make it here, as you have here it is only 2 segments, but you have more number of segments. So, this all the thing will be positive side, it will be like this, it will be like this, it will be like this, very small, you cannot make out from your eyes just looking into this, because it is DC, but so it is not exactly as a straight line, because so many segments are there. So, so many such half cycles are there. So, but it is DC, right. So, this is actually what you call this mechanism, that means every half cycle, I mean when it is going to the negative, that one side of the coil automatically connected to the your what you call next brass, right, negative side, such that your what you call that your voltage always will remain your in the positive. So, DC, since the current will be DC, and that is the some load resistance is connected here, right. So, that means your power generator, the power will flow like this. So, this is just for the sake of explanation, I have taken this diagram from a book, right, and but in the actual DC machine you have several segment of the commutators, they are basically you are insulated from each other. So, this is whatever we have. So, all this now construction of DC machine, just I will tell you what exact this thing, this diagram I have taken from a figure, right, I have taken from a book, right. So, in this case if you look into this, that just for your general knowledge. So, this is the typical line of magnetic flux, this is the shaft, this is the armature, and this is the magnetic structure, and this is the main frame, it is cut actually, it is cut, right, and this is the typical slot to allow winding coil space need, right, one of many, there may be many slots are there, and this is your N pole, these are your, and this is your S pole, that field, right, and this is the flux path is shown, and this is the air gap between faces of pole and the armature surface. So, this is the air gap is marked, right. So, this is a generator or motor by your what you call the magnetic structure, and this is the shaft. This is I have taken from a book just for the sake of your what to completeness of this brief discussion, right, and this is the main frame. Next is so DC machine consists of 2 main parts, stationary part, it is designed mainly for producing magnetic flux, right, and rotating part, it is called the armature, right, where mechanical energy is converted into electrical energy for generator, or conversely electrical energy into mechanical energy for motor. This thing you should keep it in your mind, right. Now, the stationary and rotating parts are separated from each other by an air gap, just I show in the diagram, right. The stationary part of a DC machine consists of main poles designed to create the magnetic flux. Commutating poles interpose between the main poles and you are designed to ensure your sparkless operation of the brushes at the commutator and a frame or yoke. This interpole your what you call about this commutating poles, other things we will not study for this course, you will study in your second year or third year electrical machine course, just for the sake of completeness all these things are noted down, right. The armature is a cylindrical body rotating in the space between the poles and comprising a slotted armature core, a winding inserted in the armature core slots, a commutator, a brass gear. Most all these things perhaps you will study in your machine design course also, if it is there. So, description of the parts of a DC machine. So, figure 5 actually shows the sectional view of 4-pole DC machine. First one is the frame. I will show you the diagram. The frame is the stationary part of a machine to which are fixed the your what you call this. Just see this diagram. This is actually this is the your rotation, direction of the rotation. This is the brass bar. This is the armature. Wherever you see the current, this conductor are there. Here it is basically actually here we need later. This is the just hold on. This is actually conductor. If it is a plus, that means current, we will see that current entering into the page, right. And if you use current entering into the page, then this thumb will be or what you call the direction of the current, and these fingers, the curling fingers will be the direction of the flux, right. So, similarly this side it is this side it is plus, right, this side it is plus, under S pole this is also plus dot everything is there, right. So, that means plus means current entering into the your what you call into the plane, right, and dot means it is leaving the plane. That means if it dot means current coming out. So, this is the direction of the current, and this will be the finger you are curling, this will be the direction of the flux, right. And this is your interpoles are there, we will not discuss much. These are the two terminal, this is plus, just hold on, this is your plus and this is minus, and this is the field rheostat, field resistance, this way it has been symbolized, and this is the field winding it is given, right. And this is pole shoe here, this is interpole. We will not discuss about the function why interpole is for this course, interpole is there. Then this is commutator, this is so many commutator segment, as I mean in the diagram it is few, you will have many, right. And this is your frame and this is your armature conductors, right. So, this is a schematic diagram which I have taken from a book, right. So, yeah, and if you look into that, it is 4-pole machines, right. So, you will see the 4 your brushes 1, 2, 3, 4 plus minus, right. So, this is the your what you call that your are fixed the your what you call the main and commutating poles, and by means of which the machine is bolted to its your bed plate. The yoke, the ring shaped portion which serves as the path of the main and the commutating pole, your commutative pole fluxes is called the yoke, right. So, here your if you look into that this is your what you call, this is your interpole is there, commutator is there, this is the frame, and this is the shunt pole, load terminals, field rheostat, field winding, right. And this is the direction, and this is the armature is marked here, this is the armature, right. And next is your what you call, and your the cast iron used to be the material for the frame or yoke in the early machines, but now it has been replaced by your cast steel. This is because the cast iron is saturated by a flux density of about 0.8 Weber per meter square, while saturation with cast steel is your about 1.5 Weber per meter square. Thus, the cross section of a cast iron frame is about twice that of a cast steel frame for the same value of magnetic flux, right. So, lately rolled steel yokes have been developed with the your improvements in the welding techniques. Now, next is field poles. In present day machines, it is usual to use either a completely laminated pole or solid steel poles with laminated pole shoe, right. Then commutating poles. A commutating pole, also called interpole, is similar to a main pole and consists of core terminating in a pole shoe, which may have various shapes and coil mounted on the core. So, function of this your interpole or commutating pole etc., I am not discussing here because it is first year level, just some ideas, right. So, next is the armature. The armature consists of core and winding. Iron being the magnetic material is used for armature core. However, iron is also a good conductor of electricity. The rotation of a solid iron core in the magnetic field results in eddy current, right. The flow of eddy currents in the core leads to wastage of energy and creates the your problem of heat dissipation, right. To reduce the your eddy currents, the core is made of thin laminations. This is same everywhere. If you see all the machines, you will find like this, right. So, just I have written for this thing, the armature of DC machines is built up of thin lamination of low loss silicon steel. The laminations are usually 0.4 to 0.5 millimeter thick and are insulated with varnish, right. So, this is actually that your armature of a DC machine, these are the laminations and these are the slots, right. So, where that your conductors are placed, right. So, this is the QA and this is lamination, this I have taken from a book and this is the air holes, right. and then commutator converts AC current or voltage to a DC current. Sorry, here actually no, it will be your convert is AC current or voltage to DC current or voltage, this is right. So, a commutator is a cylindrical structure built up of segments made up of hard drawn copper. These segments are separated from one another and from the frame of the machine by mica strip, right. So, this is actually your what you call some kind of diagram. This is the commutator segment, this is micanite your V ring, and this is riser from this commutator where their windings are connected to this riser or lug, right. I suggest you see in your college that open DC machine, DC motor or DC generator, and this is that commutator segment, right, and this is called riser or lug, and this is the segment, and they are all insulated, separated from each other by mica say, and this is end clamp ring and this is clamp bolt. This is just to give you, and this is the shaft, just to give one idea about this commutator, right. So, this is commutator component. So, another thing is here, if you look at the insulated copper segment, this is all insulated your copper segment, this is your what you call commutator, right, and this is your commutator lugs from here where it is connected to the winding, and this is your end clamp, and this is all this is very thin you will find and separated by mica if you look at a open DC machine, and therefore, all these things are your what you call written everywhere. So, I am not going to repeat, right. So, this is your what you call is some kind of your idea you have now. So, all these things I showed you and I told you, right. So, figure 7 actually components of a commutator, the general appearance of a commutator when completed is shown in here, right, this figure. Next is brass gear. To collect current from a rotating commutator or to feed current to it, use is made of brass gear, which consists of brasses, brass holders, brass studs or brass holder arms, brass rocker, current collecting bus bars, right. So, the brasses used for DC machines are divided into 5 classes: metal graphite, carbon graphite, electrographite and copper, right. So, the allowable current density at the brass contact varies from 5 ampere per centimeter square in case of carbon to 23 ampere per centimeter square in case of copper. So, the use of copper brasses is made up for machines designed for large currents at low voltages, right. Unless very carefully lubricated, they cut the commutator very quickly and in case the wear is rapid, right. Therefore, graphite and carbon graphite brasses are self lubricating and widely used. In your college also in the lab, if you see those brasses are made of, you will find that is a carbon graphite brasses, right. So, next is, these are all some brief discussion of the DC machine. Next is EMF equation of a generator. So, from that we will move to motor. So, let P is the number of poles and phi is equal to flux per pole, Z is equal to total number of armature conductors. So, number of slots is equal to into number of conductors per slot, that is the total number of conductor, right, and N that speed is given in RPM, revolution per minute, and A number of parallel paths in armature, EG generated EMF per parallel path in armature. Basically, DC machines are of two types, one is lap connected, another is wave. In lap connected, number of path is equal to number of poles, A is equal to P, where it is this one, this capital A is equal to P, and wave connection it will be A is equal to 2, but these are beyond the scope for this course, but you will learn in electrical machines or in machine design, right. But here for the sake of completeness we have to choose we have to consider it for numerical also. For lap connection A will be P and for wave A will be is equal to 2 always, right. Now, suppose EMF generated per conductor will be say d phi dash by dt volt, right. Now, flux cut per your conductor in one revolution will be d phi dash will be P into phi, right, because phi is flux per pole. So, d phi dash will be P into phi Weber, right. So, number of revolutions per second, because we have taken speed RPM revolution per minute, if it is revolution per second it will be n by 60 then. Now, time for one revolution dt will be just reciprocal of this, dt will be 60 upon n second, right. Therefore, EMF generated per conductor, this is your d phi dash by dt. So, it will be d phi dash is p phi and dt will be 60 upon n, that is p phi n upon 60 volts, right, straightforward. Now, for a lap winding generator, I told you number of parallel paths will be A is equal to P, and so number of conductors in one path will be Z upon A, right, because you have a number of parallel paths. So, Z upon A. Therefore, voltage induced will be P into phi into n upon 60, that means this much into your Z upon A. So, that is equal to phi Z n by 60 into P by A volt, right. Now, for a wave winding actually number of parallel paths always 2, A is equal to 2. So, if you put here A is equal to 2, right, then that means number of conductors in one path Z by 2 is equal to Z by A, right. So, I mean it is for wave connection. So, it will be Z by 2, write Z by A and A is equal to 2. So, it is easy to remember again, it is phi Z n by 60 into P by A, right. So, for lap connection A is equal to P, and for wave connection A is equal to 2, right. So, therefore, Eg is equal to phi Z n by 60 into P A volts. For lap winding A is equal to P, and for wave winding A is equal to 2, right. This thing for numerical part you have to keep it in your mind. Next is DC motors. Philosophy is same. So, electric motor is a machine which converts electric energy into mechanical energy. This is DC motor. The application, because of their inherent characteristic, DC motor find extensive application in steel plants, paper mills, cranes, textile mills, printing presses and excavators, right. And advantages, DC motors possess the following advantages: high starting torque, speed control over a wide range, accurate stepless speed control with constant torque, quick starting, stopping, reversing and accelerating. These are the advantages for DC motor. Disadvantages, cost is high, higher operating and maintenance cost because of the commutator and your brush gear, right. Now, principal operation of DC motor. So, figure I will come. So, figure 9 in general illustrates the principle. Next I will show. Figure 9a shows the field set up by the poles, and figure 9b shows the conductor field due to flow of current in the conductor. Now, this is actually figure. Now, here before anything we do, we have to understand little bit. Now, here when this is my N and N's pole, this is the your what you call, this is the flux line is shown here, right. And second thing is this is the plus, that means conductor actually, that is this is the conductor, and plus means the current is entering into the plane. So, if the current is entering in the plane, that this is the direction of the current, the thumb, look at my thumb, and if you curl the finger like this will be the direction of the flux. That is why the flux direction, if you see here, all these things are clockwise, all these things are clockwise. So, plus 1 you just make this your thumb is right hand rule you put, and your thumb is your what you call the direction of the current, because it is going into the paper, right, or into the plane, and this is the direction of the flux. And similarly, if you take a your what you call, suppose a dot, suppose this is the conductor, suppose dot, then current actually what will happen, current actually leaving the plane or leaving the page. So, move it upward. So, in that case the direction of the flux will be anti-clockwise, direction of the flux will be anti-clockwise, say this one, just opposite to this, just you will use the thumb rule. So, that means whenever whenever you are bringing this conductor, say bringing this conductor, it is given ANS like this, when you are bringing this conductor here, then what is happening, the flux, this is your N to S it is going, and this upper side if you see, this is clockwise. So, that means this if this is clockwise, so this upper side it is actually additive, and the lower side it is subtractive. Similarly, here the lower side is additive because it is anti-clockwise, and upper side is subtractive. That means force actually acting downwards here, and here it is upward, right. So, here it is upward. So, that is the first thing, this thing we have to understand before that mechanism of rotation. So, that means because here it is, if you look into that, this is the direction, and if you put here, this is also direction. So, both the flux will be same direction, this one and this one. So, finally, it is additive. That is why it is your what you call force is acting downwards, and just opposite here, that force is acting your what you call upwards, right. So, that means when conductors are placed carrying current and placed in the magnetic field, this is your, that is the plus and this is the dot, I told you how it is, right. So, all these things actually whatever I said, all these things are written here. So, not further I am explaining this, right. So, that it is written additive and subtractive, everything is written here. Now, this clearly shows that conductor in figure has a force on it which tends to move it downward, and thus the force acts in the direction of the weaker field, right, whatever I showed in the diagram. When the current in the conductor is reverse, that is the second diagram, right, the force is also reverse, and it is your what you call force is acting on the downwards, that is weaker field this side and here also, right. So, now generally the force developed in the conductor is given by that F is equal to B I L Newton N, right, N is, here it is given Newton. So, B is the flux density Weber per meter square, and I is the current in conductor say ampere, and L is the length of the conductor in meter. Now, consider the magnetic field of a DC motor in which there is no current in the armature conductors. The lines of flux path is shown in figure 10. So, just if you see the diagram here, that these are the conductor plates, and assume the conductor is not carrying any current. So, this is the flux path for N to S, right. This is conductors and this is your armature. So, distribution of line of flux in a motor due to magnetic field only, right, but conductors carrying no current. So, if it is so, now let us see the conductor is carrying current, this side is plus, look at the my cursor, this side is the plus, this side is your what you call dot. So, if you look into this and just your what you call that follow, you apply the same your right hand, if you apply that your right hand rule, right, then you can easily find out that your what you call the direction of the flux, right. So, in this case is N to S, naturally this is the plus, so your as per our convention current entering into the plane. So, this side will be your what you call, this side will be your additive, right. So, and force will be acting downward, and this side your what you call lower portion will be additive, force will act upwards. So, here everywhere downward, everywhere it is upward. So, from intuition you can say that it will start rotating in your what you call in that clockwise direction, right. So, this is your just same philosophy, that is why previously I showed the diagram. This diagram I have taken from a book, right. So, now if the armature carries current, each of the conductors will produce a magnetic field which when superimposed on the main field causes a distribution of magnetic lines of flux as shown in your figure 1. So, this is the thing I told you, basic philosophy is like this. So, the magnetic field that is your in figure 11 is said to be distorted since the lines of force no longer follow approximately straight path, because this is distorted because it is not following any straight line path, right. So, this line of force have the property of tending to shorten themselves, right, so that they may be regarded as being in tension. So, each conductor in figure 11 will experience a force, I told you how it will experience. Since these conductors are embedded in slots in the armature, the latter is caused to rotate in a clockwise direction, whatever I told you, right. So, it will rotate in the clockwise direction, and these conductors are placed in a slot. Next is that back EMF of a motor, generally referred to figure 12. Now, this is a motor, right, and this is, suppose you take your plus that conductor, right, and current is entering into the plane. So, if it is entering into the plane, then here it will be what you call, if you look into this, this is your again the same philosophy, this is the plus, current is entering into the plane. So, move it like this, the thumb is the direction of the current, then you just grasp that your what you call the finger 1, this is the direction of the flux, that is why this is shown here, right, and this N to S, the flux line will be N to S. So, naturally your what you call this, the force is acting your what you call this from stronger magnetic field to the weaker one. So, this is the direction of the force, and naturally this is the direction of the motion, right. So, in a DC motor, when the armature rotates, the conductors on it your what you call cut the lines of force, just hold on, cut the lines of force of magnetic field in which they revolve, right. So, that EMF is induced in the armature as in a generator, right. So, this is the motoring operation and this is the armature. So, this is the same philosophy, and this is only N pole is shown here, and this is what you call, we have to think about the back EMF, right. So, in that case what will happen, the induced EMF acts in opposition to the current in the machine and therefore, to the applied voltage. So, that it is customary to refer to this voltage as the back EMF. Now, as per the your what you call for your transformer, we have seen that this can be deduced by Lenz's law, which states that the direction of an induced EMF is such as to oppose the change causing it, which is of course the applied voltage, right. So, that means that means if you look into that, this is the plus direction and this is the minus and this is my back EMF EB, right. If you look into that IA actually current your what you call, instead of your going into the your negative polarity, that current actually leaving from this one for the motor. It is just a schematic diagram, but when you are connecting a supply voltage you will see that, right. So, that is your what you call the meaning here. This can be deduced by Lenz's law, which states that the direction of an induced EMF is such as to oppose the change causing it, which is of course the applied voltage, right. So, that is why the magnitude of back EMF can be calculated by using formula for the induced EMF in a generator. Same formula, back EMF will be same formula, EB is equal to phi z n by 60 into P by A, that means Zp upon 60A phi into n. So, Zp upon 60A is a constant, right. So, EB can be written as K into phi n for motor back EMF. Therefore, K is equal to Zp upon 60A, because Z is a constant, P is a constant, A is a constant, and so therefore, it is a constant, right. So, this is actually your what you call back EMF. When you will take numericals, at that time you will find things are much easier, right. So, in this case your therefore, back EMF is always less than the applied voltage. So, although the difference is very small when the machine is running under normal conditions. So, it is the difference between these two quantities which actually drives current to the resistance of the armature circuit. We will see later. If the armature of if the resistance of the armature if the armature resistance is Ra, back EMF is EB, applied voltage is V, right. Then we have this equation V is equal to EB plus IA Ra. We will see this later, right. So, thank you very much, we will be back again.